Hello, this is the second episode of my geometry talk series. In this episode, we will continue our discussion of the simple geometry problem presented to you in episode 1. Here, a variation and a generalization will be discussed. In episode 1, this problem was solved. Given two equal radius circles that are both tangent to the hypotenuse of a right triangle, and each is tangent to a side of the triangle. So what the value of R is. In episode 1, we proved that these two circles do exist and are unique. We also found the radius R to be this one. Now, in this episode, first of all, let's rewrite this part as this one. Because we can take one of the C out and multiply this one by A plus B and add to the remaining C, we have this. So this version is important to our later discussions. So the question in this episode is, what if these two circles are tangent to one of these two other sides? In this figure, these two circles are tangent to side A. The same technique can be applied to find the radius of these two circles being tangent to side B. The existence and the uniqueness of this version are the same as the one we discussed in episode 1. So what is the value of R? This is what we are going to find out. Is that simple? Yes, it's rather simple, but the technique is slightly different from the one we used in episode 1. So let's do some constructions. From each center, we drop a perpendicular to side A, side B, and side C. For this circle, we drop a perpendicular to side A and side B, but we did not drop a perpendicular to side C. Why? Well, the question is, if we drop a perpendicular from this center to this side, what benefits could it have? So we drop a perpendicular here. How do we find the length of this part? Which is not so easy. Instead, we construct a common tangent through this tangent point of these two circles. This common tangent is parallel to side B and intersecting side C at a point. From this point, we drop a perpendicular to side B. So here we have a right triangle. This right triangle has a side length U and side length V. Both are unknown. So what we're going to do is find the length of U and V, and then later find the length of this one. We are done. So let's start from the perpendiculars. We know through the construction of these perpendiculars, the length here is the radius R, unknown. Therefore, this is a square, R, R, and R. The distance between these two centers is 2R. Therefore, we have a rectangle, R, 2R, and R. So on side A, the remaining length can be easily calculated as A minus 3R. Why 3R? It's the sum of R plus 2R. So the length of this segment is A, minus 3r. Due to equal tangent from this point, this segment is equal to this segment. So the length of this segment is also a minus 3r. So the division of side C into 3 line segments, and one of them is known. Now let's take a look at the length here. Because this is a common tangent, it's parallel to side B for sure. Therefore, the length going from this point and this point is 2r. We let this point to be E, this point be F, this point be A, B, and C. The right triangle A, E, F is similar to the given triangle A, B, and C. Therefore, due to the property of similar triangles, we know U over 2R is equal to B over A, which is here. By the same reason, the similarity of triangle AEF and ABC provides us with V over 2R is equal to C over A. We have here. So the length of this segment U and the length of this segment V is represented by the side lengths A, B, and C, and the unknown radius R. Therefore, we have U equals 2R times B over A, and V equals 2R times C over A. We're almost done because we know U and V, the remaining is this segment. Because we mentioned that this is a rectangle. This is a common tangent. And this common tangent is, of course, parallel to side B. Now, because we know this segment is R, this segment is U equals 2R times B over A. So this segment is B minus the sum of R and 2R times B over A. Because this is a rectangle, this side length is also B minus the sum of R and 2R times B times A. Now, the next step is, again, equal tangent. This is a common tangent. And side C is also tangent to this circle. Therefore, the tangent length from this point to this circle at this point, and the tangent length from this circle at this point to this circle are equal. Therefore, the length of this segment is also B minus the sum of R plus 2R times B over A. So in this way, just like we did for in episode 1, we divided side C by some segment. The length of this segment is equal to C. Therefore, C is equal to the sum of A minus 3R, B minus R times 2R B over A, and 2R times C over A. This is the result. Now, simplifying this, we get this. It's very simple. We move B with A and get all of those R terms together. We have this. We are almost done because the unknown value R is in a single term. We copy the expression here. Now, again, we use the same trick as we mentioned earlier. 2 plus B minus over A is equal to 2A plus B minus C. So we make this 2A into A plus B minus C. This term is very crucial to a uniform and symmetric representation of our result. And then solving R yields this formula. This is our result. This is our result. Therefore, the radius of the two circles tangent to side B is this. You do the same calculation. How? If you don't want to do it, you just imagine that you make these two circles to be tangent to side B. You follow essentially the same procedure by replacing A by B. You get this one. So the calculation of R of A, R of B is the same. Now look at how similar it is. A plus B minus C, A plus B minus C, A plus B minus C. And for side A, we have, for side B, we have B and B. So what if the circle are tangent to the hypotenuse? This is the result. And we add C to here and subtract A, C. In other words, we add a C and subtract a C. We get this. Why we need this? Because we need to make a term, A plus B minus C. So we copy all of our results. Are A, the radius of those two circles tangent to side A, to side B, and to side C here. As you can see, A plus B minus C appear in every result. And for RA, we see AA here. For RB, by replacing A by B, we have B here. We have C and C here. So this form is more symmetric than the previous form we discussed in episode 1. Therefore, we solve a variation of the problem discussed in episode 1. Then we ask a simple question. We worked on right triangles. Can we do the same for arbitrary triangles? In other words, can we generalize the results to an arbitrary triangle? Now let's consider an arbitrary triangle A, B, and C. This triangle has an incircle with center O. The radius of incircle is R. In that way, we have to change these two equal radius circle to have radius D. So these two equal radius circle in this diagram are tangent to side C. Their center U and V must be on the bisector of angle A and a bisector of angle B. These two bisectors intersect at the incenter O. Now, let's connect a line segment U and V. Because these two circles are tangent to each other with the same radius, this is going to be 2D. The distance from the center V to side C and the distance from U to side C are equal. Both are D's. So in this way, the altitudes of triangle OUV is R minus D. The altitude of triangle OAB on side C is, of course, R. So we are almost done. So from the results of triangle OUV being similar to OAB, we have 2D over C is equal to R minus D over R. So we have only one unknown, D. Notice here, R is the radius of the incircle, which is known when a triangle is given. So solving for D, we have this. Now we have two terms with D, so we move CD to here and factorize and take out the factor of D, we have this. So for an arbitrary triangle, the unknown radius of two equal radius tangent circle is C times R over 2R plus C, where R is the radius of the incircle. Well, this is such a simple solution, right? Very, very simple, much simpler than the right triangle version. Furthermore, it's so easy to find D. However, you may not be satisfied because previously we represent the radius of the two equal radius circle by the signs A, B, and C. However, in this case, we represent D by the use of the radius of the incircle. If you are satisfied with this incircle radius representation, that's fine. But what if you don't like to do it? Instead, you are so stubborn that you have to represent D by the use of three sides A, B, and C. No problem. We can easily find the radius of the incircle by the use of A, B, and C. You probably have learned it in your high school geometry textbook. Triangle ABC has an incenter O. So this three triangle OAC, OBC, and OAC, these three triangles cut the given triangle ABC into three. The sum of area of these three triangles is equal to the area of the given triangle. Therefore, we have the area of triangle ABC is equal to the sum of area of triangle OAC plus the area of OCB plus the area of OBA. Now, the area of triangle OAC is simply half of A times R. The area of OCB is half of R times A. The area of here is the length of C times R, which is exactly the radius of the incircle. So we have this. And then taking 1/2 of the R outside, we have this formula. So let S be A plus B plus C over 2. We have the area of triangle of ABC is S times R. Therefore, the radius of the incircle is the area of ABC divided by S. In this way, we are able to calculate incircle radius by the use of three sides A, B, and C. So we plug the incircle radius value into the results for D we obtained earlier. We have this. Notice here we use area of triangle ABC, which is calculated from ABC. Now notice here we use C here, only appear twice. It's easy to see that if these two circles are tangent to side B, you replace C by B. And if these two circles are tangent to side A, you replace C by A. then we're done. This is the result. So the unknown radius on C on B on A can be written as this. It's even simpler than the right triangle version. Now you know the area of triangle ABC is this one, the square root of S times S minus A times S minus B times S minus C. So we have very, very elegant results. Let's verify something. What if triangle ABC is a right triangle with side C being the hypotenuse? In other words, angle C is 90 degrees. So before we go on, let's refresh a trick you probably have learned and used so many times. So A plus B plus C times A plus B minus C. We could group A plus B together. In this way, we have x plus y times x minus y. We have x squared minus y squared. Now, because C is hypotenuse, so C squared is equal to A squared plus B squared. So we replace C squared by A squared plus B squared. The result of this product is 2AB. Then let's just take a look at how do we calculate dA and simplify it if the triangle is right triangle. We know the right triangle area is A times B over 2. So we replace this area by A times B over 2 and replace this one by the same. So we have, going from here, we have this. Now, here we have A plus B plus C. According to this result, A plus B plus C is equal to 2AB over A plus B minus C. We have this. Now, from here, we have AB over 2. We could take 1 over 2 times AB here and here. Then these three terms are cancelled. We have this. A here. We have 2 here plus 2A, this A, over A plus B minus C. Now, these two can be taken out as well as the A. We have this. We have this formula. And finally, do some simplification, we have this. And oh friend, we saw it in the right triangle version. So, going from the general case to a special case is pretty easy. Let's do a sidestep. How can we go from the Heron's formula to half of A times B if angle C is 90 degrees? Let's take S out from Heron's formula. That is replacing S by A plus B plus C over 2 here, 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 and here. Now just take a look at this term. It's going to be A plus B plus C minus 2A. If we take A above, then A minus 2A, it becomes B plus C minus A. So this term goes here. This term is simplified to this term. So this term and this term. So these 4 2's is 2 raised to the 4th power. Taking the square root, we have 1 over 2 squared. Now we know if the triangle is a right triangle with hypotenuse C, then these two terms is 2 times AB. We can also show that the product of these two terms is also 2AB. Let's take a look at it. B plus C minus A plus C minus B. Now we see both terms C has plus. So we move C to the front. So this one is equal to minus A minus B. For this one is plus A minus B. So again, we apply the trick minus y times x plus y is equal to x squared minus y squared. Now, because c squared is equal to a squared plus b squared, we have, again, 2ab. So we verified that going from Hurlong's formula to a right triangle, which is a times b over 2. So this ends episode 2. In this episode, we successfully derived the radius of the two equal radius circles that are tangent to each other and to a common side. And each of these circles is tangent to a leg. The results are very simple. We also rewrite the results in a uniform and symmetric way. And this problem can easily be generalized to general triangles by the use of the radius of Incircle. The existence and the uniqueness of the general case can be proved in the same way as we did in episode 1. And this ends our episode 2. In the next episode, we will talk about 2 simple Japanese temple geometries. So through these 2 episodes, I hope you understand that when you work on a simple problem, always think, is there some way we could extend it to a more general form? That's the way of working in science. So let me stop here and hope to see you next time. Goodbye.